right. There is a quiz. The correct answer to question 2 is E for Edward. All right. So for the people on YouTube, although I have no confidence that you're on YouTube either, but the correct answer is E if you're watching. If you're not watching, you did not get the correct answer, or you could guess. So okay. So I want to do the code for heaps. So just to remind people of how those things go. So again, very quickly. Yes. So what? No. So what we're trying to do here is to implement a priority queue. So that means I want to be able to insert, I want to be able to compute the minimum, and I want to be able to get the minimum and also remove it from the data structure. And you could do it with a list. We have done it with a list, but you can also do it with a heap. And the idea of doing it with a heap is that allows you to do both insert and extract min in all of log n time. So what's a heap? One way of thinking about it is it's a way of storing data in an array, but in a particular order, right? So the data still goes in an array. It's just that you interpret this array as this complete binary tree that satisfies the heap order property, right? So that means that the smallest element is at the top, and that means the smallest element is on the extreme left. And then you store the next 2 elements, and then the next 4 elements, and so on, right? So it's like A, and then BC, and then D, E, F, G, and so on. And if you arrange them in this tree structure, then what you see is that the children of each parent are larger, than or equal than the parent. So that's not quite the same as saying that it's sorted, although if it were sorted, it would be a heap. Does that make sense? Why is it the case that if it were sorted, then it would be a heap? Yeah.
You're still preserving the stack.
The heap order property would be, yeah, exactly, because if it's sorted, well, the first element is the smallest one in the sorted array. Yes, it is. Sorry, let me try to. Okay, maybe that's going to be better. So the smallest is in the right place, and then the children would, so 2 and 3 would follow 1, so they would be larger than 1, sorry. And their children is going to be larger still because it's a sorted list. In fact, what you see here is that this heap happens to also be a sorted array. But it didn't have to be. So for example, you could change the places of 10 and 11, and it should still be a heap because every child is going to be larger than the parent still, but it wouldn't anymore be exactly sorted. Does that make sense? So a heap is easier to maintain than a sorted array. In fact, like kind of, at least kind of insofar as far as we know, in order to maintain the array as sorted, you need O(n) insertion, right? Because you need to find the right place for the new element, and that potentially takes O(n) comparisons. With a heap, what we saw last time is that you can do it in O of log n. So, okay, so how do we do it? So the idea is so I'll just recap the concept and then we'll do it in code. So the idea, if you want to do something like insert the 14, is you insert it at the end of the heap and then you percolate it up. So if you insert something like the 14 at the end of the heap, what happens is it's not a heap anymore necessarily, because it might be the case that this 14 is actually smaller than 31, its putative parent, right? But it's almost a heap. The only thing that messes things up is the 14. And then you can say, okay, I'll percolate it up. So what it means is I'll swap the 14 and the 31, and then I'll see if the 14 is still in its right place. No, it's not, because 14 is also smaller than 21. So I'll swap the 14 with the 21 and so on until I don't need to percolate it up. So that is how that would go. Does that make sense? So that's insertion. So extract min is like this. So if you had something here at the top, you can extract it. Then it's not a heap. It doesn't have a root anymore. So what you do is you take the last element from the heap and you put it as the root temporarily, and then you percolate it down. So here, 32 used to be at the end. We replaced the min, which we extracted, with 32. And then we percolate 32 down. The way it works is we say, okay, 32 needs to be swapped with its smaller child. So with 16 in this example, with the smaller child, because if you swap it with the larger child, so if you swap 32 with 21, then 21 is not actually a valid parent for 16. But if you swap it with a smaller child, that would not be an issue. So that's like this. And again, you percolate 32 down. So in this example, both with extract min and with insert, we percolated all the way up and all the way down. It doesn't have to be this way. You just percolate until you don't need to anymore. All right. So the short of it is, why is this efficient? Well, it's because the height of this tree, meaning the number of levels, is log n, specifically log 2n approximately, as we derived last time. So that means that all you need is log 2n swaps in order to restore the heap order property. So that means that both insertion and extract min are O of log n operations, as opposed to kind of the bad O of n operations that you would have otherwise. Make sense? So, okay, so that's conceptually what it is. So here I want to look for a while at an implementation. And again, I kind of told people this just talking to people, but like what's true is that what's really useful is for you to do it. It's not super useful to look at it. at the same time, I'll try to make it useful in the sense that, you know, I tried to make the code nice. But other than that, like, it's not kind of super informative, but I'll walk you through the code a little bit. So what we have is we have this heap class, and it starts with a list that just contains none. So that's the placeholder. If you remember, we wanted to make it so that at location 0, at location 0, we don't have anything, and we store the first element at location 1. And that's just because it happens that those functions are more convenient if we do it that way. So if you remember, get left child index, get right child index can work like this. So it's like twice the parent index and twice the parent index plus 1. So we did the math last week. And if you have a child index, then you can get the parent index by doing integer division by 2. So here, just have like a helper function for swapping elements at index 1 and index 2. So other helpful, so those are just like helpful helper functions that you can have. So I might like to know whether there is a left child or there is a right child. So for the nodes at the bottom, that might be an issue. And the way I'll find out is whether the index of the left and the right child are not larger than the size of the heap. If they're larger, that means that we don't have them. If they're smaller, it means we do, because the heap is complete, right? So everything is full between index 1 and index self.size. Does that make sense? So, all right. So has parent is like, that might be overdoing it, right? So every node has a parent except for the root, which is index 1. So one way to ask it is, you know, like, is index larger or equal to larger than 1, and then it has a parent, or is it not larger than 1 and then it doesn't have a parent? So, okay, but just like for symmetry purposes, we also have like a has parent function. So separately from that, we want to be able to get the left child, we want to get the right child, and we want to get the parent. So with that, we can look at the insert function. So the insert function appends the value to the end of the heap, right? So that means on the extreme right of the last level. And increases the size. And now we percolate up. So the percolate up is done in the heapify up function, right? Does that make sense to everyone? Questions? Okay. So how do we percolate up? So we are currently processing the element at index self.size. That's the last element, right? So the rightmost element in the bottom level. And now we're saying, okay, so if it has a parent, and also the parent is larger than the element, that's bad, they need to be swapped. So we swap them. And we say that the new index of the element we're looking at is the index of the parent. Is that good? So we're percolating up, right? So we're saying do we want to swap the 14 with the 31? And then if we do swap the 14 with the 31, we want to be updating the index of the current node being processed to the index of the location over here, which is the new location of the 14. That's it. We just keep doing it while there is a parent to swap with. If there isn't, that means that the element is already at the root and there's nothing more to do. And the parent is smaller than the current element, larger, sorry, than the current element, in which case we need to swap. All right. So here is extract min. So extract min says, okay, I want the minimum. That's going to be the first element in the array. So that's self.heap at 1. So remember, the heap is just a list which initially has the one element none, right? So that's the array in which we maintain all the elements. So now what we do is we say, okay, put the last element in the heap at the root. So put the element at the end. So that's heap at size. That's the last element because all the elements go from 1 to size. Put it in self.heap 1, and that's because we start with 1, right? And now we remove the last element because we already copied it to location at index 1, so don't need the element at the end. Reduce the size by 1 and percolate the new root that you just copied down the heap. So heapify down is get me the index of the smaller child, and if necessary, swap the current node with the smaller child. Okay. So that's it. Makes sense? All right. Questions about any of this? I'm going to a new topic, if not. All right. I now want to talk about optimal paths in graphs. So here's the big, yeah. Okay. It's not different from a binary tree. It's a kind of a binary tree. Now, usually, so binary trees are going to be like in a supplementary lecture that's going to be posted like tomorrow, probably. So usually you store trees the way you store graphs, right? So the heaps we store in an array. The reason we're able to do that is that a heap is a complete tree. So that means that you can read off the tree just like level by level and know exactly where in the array the node should go. If there were missing nodes in the tree, then you couldn't do that. Then you couldn't do that.
So it's like a complete binary tree?
A heap is a complete binary tree that satisfies the heap order property. Yeah. So, but like, again, kind of, I think there's like two separate concepts there, right? So like one is, is it a tree thought about like abstractly in the sense, yes, you can arrange it in a tree. Is it represented the way trees usually are represented? Well, no, because usually trees are not complete, and then you can't store them in an array. Or you could, but there would be all sorts of complications. Yeah.
Are we doing like heaps in C as well? Or
Who is we? So some of us are. Okay. So yeah, like I'm not, so, okay. So like without joking, can I ask you to implement like it wouldn't be reasonable to like, say like implement like all of heaps in C on the exam. Can I ask you to do kind of part of it in C? Well, like of course, like the same way that I could ask you to implement any kind of algorithm that you're not even familiar with in C. I could certainly ask you to implement an algorithm that I covered in class in C. So, okay. Yeah. Sorry, can you speak up? So, so heapify down is, so it's the same as kind of percolate down, right? So what we're doing is we're starting with, let me close this. So I'm starting with the root not being necessarily the correct root, and then I'm percolating it down. So for example, here 32 is being percolated down until the heap order property is satisfied. So I want several things. So definitely I want the smallest element to become the root. But I also want the heap order property to be satisfied in general. And the way to do it is because the only thing that's possibly wrong is that the 32 is in the wrong place, is I just keep pushing 32 down. The way I do it is I swap the current element with the smaller of its children. So here I swap 32 with the smaller of 21 and 16. So 16 is now here and 32 was swapped with it. And now again, 32 has two children. One of them is the smaller one, so 19 is the smaller one. And it's also smaller than 32. So I swap 32 and 19, and now 32 is here. Say again? No, 16. So like 32 already replaced whatever was at the time. No, like in this picture, we imagine that 32 already replaced the old minimum. So the removal of the minimum already happened, and 32 overrode that minimum. Okay. All right. So shortest paths. So basically, if you have a graph, so a bunch of nodes that are connected, in general with edges that have weights, but it could be that the edges do not have weights, that would be fine as well. What you might like to do is to find a path where the sum of the weights or the sum of the weights on the edges is as small as possible, right? So for example, if you want to get from 1 to 5 over here, and you want to pay as little as possible, then what might make sense is to go here, here, here. So that costs 11. As opposed to, for example, going like this, which would cost 12. Or going like this, which would cost 20. Right? So there's multiple paths you can take, and you want the cheapest path. So if the edges are unweighted, meaning every weight is just equal to 1, then people would say the shortest path, meaning the path with the fewest edges. That's the same as the cheapest path, where every edge costs the same. And like you might imagine, obviously kind of or whatever, like intersections on a map that are connected by roads, and each road segment costs something. It could be the average time it takes to traverse it, or it could be the distance, or it could be some combination, stuff like that. right? So that would be kind of the obvious application. There's not obvious applications as well. So how do you do it? So let's dwell on this for a second. You could imagine, well, I'll just try looking at all the possibilities and pick the cheapest one. The problem is that there is a lot of possibilities. As it turns out, there is an effective algorithm for this thing. So analyzing how effective exactly is going to be a little bit annoying, but there is an effective algorithm. And the insight here is if you want to get from node A to node H here, and if you have to go through node E, which in this case you have to, then you can break this problem down into what's the cheapest way to get from A to E, and then what's the cheapest way to get from E to H. Right? So that's just the intuition. You don't in general know what this kind of node E is that you have to go through. We'll see how that intuition is used later on. Right? Of course, like if the graph is this small, you can just stare at it and say, oh, like E is the bottleneck, you have to go through E, obviously. And then you can break the problem down. In general, like you have a huge map that's like maybe not even two-dimensional, right? So you couldn't just eyeball it. But that's kind of the intuition. All right. So, okay. So here's the algorithm, and we'll see how it uses the intuition in a second. So first, like that's like one of the algorithms that's not super easy, although it's just one slide. So it's Dijkstra's algorithm, so named after Edgar Dijkstra, the Dutch computer scientist. So that's his name is Dijkstra. Here's what we do. So we maintain a set S of nodes that we explored. And this is source, not source. And we start with the source node. And then we also maintain D of V, so the shortest path from the source node to V. And the shortest path from source to source is just 0 because you're already there. So initially we say we have visited the source node and we know that D of source is equal to 0. What we do now, it's kind of similar to the kind of thing that we saw before, but that's just in spirit. So it's a quite different algorithm, actually. So what we do now is we expand the set of visited nodes by 1 every time. And we do it in such a way that we're able to actually know what the shortest path to the newly visited node is. Why it is that we know, we'll see in a second. But that is what we do. So we look for an unvisited node such that du plus the edge from U to V is as small as possible for some node U that's already been visited. So we have a set of visited nodes, and we're saying, I want to go from a node that was visited to one that wasn't visited. And I want it to be the case that du plus the edge from UV is as small as possible. And then d of v is just du plus the edge from UV. This turns out to be correct. So the central insight of the algorithm is that this turns out to be correct, that d of v is this. So the challenge is that you in general don't know like d of g or something, right? So d of g is what's the shortest path from A to G? And the answer is, you have to look at all of them, right? So the trick is you have the visited nodes, and for the visited nodes, you keep track of those are the shortest distances, I'm sure of it. And then you're saying, I want to go from the visited nodes to one that's unvisited. And we select the one that's unvisited in such a way that we actually know the distance to the new one as well. So here's why it works. So that's like not an easy argument, but that's just life. So imagine that we have this set of visited nodes. So this would be S and U and X. So the gray is the set of visited nodes. And now we're saying, okay, imagine that for the visited nodes, we're solid. For the visited nodes, they were visited, and we also know the length of the shortest path from the source to every visited node. And now I want to say, okay, like, is V a good candidate to add? And the argument is yes. If it's the case that the shortest path from S to U plus the edge from U to V is as small as it could possibly be. The reason that's the case is that it couldn't be that the distance between S and V, the shortest path between S and V, is smaller than S to U and then U to V. And that's because, well, how would it go if it were the case? Well, it would be that you go from S to some visited node X to another node Y, and then to V. And that's because, well, it couldn't be that you go directly from S to V, and that's cheaper because you would have seen that. Then there is S is visited, and there would be an edge from S to V. So that's out. That couldn't be, right? It couldn't be that you go from S to X, either directly or indirectly, and then to V, and that's cheaper because, again, you would have seen that. It would be the case that there is an edge from S to X and then from X to V that's shorter in sum than S to U and U to V. We selected V precisely so that S to U plus U to V is as small as possible. So the only possibilities that's left is that somehow it's cheaper to go from S to X and then to X to Y and then Y to V. Well, that's obviously not the case because S to U plus U to V is smaller than S to X plus X to Y already. Going from Y to V is just going to add insult to injury. Right? So we listed out here all the possibilities in which it wouldn't be the case that the cheapest path from S to V is first to go S to U and then the edge U to V. We excluded all those possibilities. So that must mean that it's true that if you select V such that there is an edge from a visited node U such that S to U plus U to V is as small as possible, then the shortest possible path from S to V is via U. That's the argument, right? So what this proves is that if we do it like that, so we start with just S is visited, and then we expand the visited set one by one in such a way that S to some visited node plus the edge from the visited node to V is as small as possible, we will have correctly recorded the shortest distance possible from S to V, where V is the newly added node. Yeah.
So if you start with all you know is the first node, like the source node,
yeah,
shortest path is obviously 0.
Yeah.
Then does that mean the only node that you can add at first is going to be the shortest path? Or like
the edge, yeah, like the smallest edge from S to whatever is the thing that you can definitely add. And that makes sense because it's definitely true that if you look at all the edges that go out from S and you find the shortest one, well, that is how you get to that node. That's definitely cheapest.
And then from there, you're just like looking at the shortest edge from that remaining graph, like the whole.
So the shortest edge so the shortest sum, right, of S to U, where U is inside visited, plus the edge from U to V, where U is visited, but V is the new one. Does that make sense? Questions? So again, what we do is we have this set of visited nodes, and we expand it one by one, and we select the node that's outside the set in such a way that S to U plus UV is as small as possible. Yeah.
Can you like maybe show like how it works, like on the A to H, for example?
Yeah. So so we start with so S is initially 1, and D of 1 is 0. Because to get from 1 to 1 is 0. So now we're saying, so the visited set is just 1, and we're looking for an edge from the visited set to outside of that. So that means that our choices are this or this. Right. So the shorter path is 3. So that means that we add 2 to visited, and D of 2 is 3. So now the visited set is 1, 2, and we're looking for an edge outside the visited set to a new node. So the possibilities are 3. That would cost 10, right? Because 3 plus 2, 3 plus 7. Another possibility is 6. That costs 13. And another possibility is 6 this way, and that would cost 5. So that's the cheapest one. So we visit 6. And D of 6 is 5. So far, what we found is like the distance from 1 to 1 is 0, and the distance from 1 to 2 is 3, and the distance from 1 to 6 is 5. So it's like it didn't have to be this way, right? So 6, for example, you could get to it like this. It's just that it would be more expensive. Yeah.
So to determine that 6 is like that 5 is now the shortest path to 6, do you have to check both the edges connected to 2?
So we have to look at the cheapest path from the visited set to outside the visited set.
Okay.
And that turns out to be 0 plus 5.
Right.
Okay.
Instead of 3 plus 7 or 3 plus 9.
That's right. Yeah, that's right. Yeah. So okay. So what stuff do we have going out? So the visited set now is 1 to 6. And what stuff do we have going out of the visited set to new nodes? In fact, everything. So okay, so we don't have anything interesting going on because so far we just went from 1 to 2 and 1 to 6. But anyway, so we have 3 plus 7, so we have 10. We have 12. We have 7. We have 13. So 7 would be the cheapest. 4. Right? So now it's going to be a little bit complicated to keep track of. So basically, the only options that we have are 3 or 5, and we need to figure out which of those we want, right? So 3 would cost 10 this way. It would cost more this way. It would cost 5 plus 2 plus 5 this way, so that's more. So 10 is the cheapest way to get to 3. And then to get to 5, there's not a way to do it cheaper than 10. So that means that 3 would be added next. And now we need to look at, okay, so to get to 3 costs 10, to get to 6 costs 5, to get to 4 costs 7. So what's the cheapest way to get from the visited set, which is everything except 5, to 5? Well, you just need to kind of like list it out, but I believe the cheapest way would be 11. Right, so that's cheaper than the 12. Everything else looks more expensive. So the cheapest way is d of 3 plus 1. So that means that d of 5 is 11, and we now have visited 5 as well. Make sense? And you can kind of see that, like, that wasn't, like, so, like, even with this graph, it would be kind of annoying to do it if you didn't do it algorithmically, right? So, like, so I did it, like, semi kind of eyeballing because, like, I can't exactly run a for loop in my head. But, like, you can see that, like, maybe you wouldn't have seen that from 1 to 5, the cheapest thing is 11. It's all right. So what's the complexity? Well, the complexity, unfortunately, depends on the implementation details. So the simplest implementation is you just have this you have this set of visited nodes, and you just try every possible node every time, and you see which sum of du plus edge from uv is cheapest. So if you look through, in the worst case, all the possible vertices every time, and you add n vertices, that's n squared, right? So you could try to be kind of a little bit of a cheapskate there and say, first I'll look at n, and then I'll look at n minus 1 candidates, n minus 2 candidates, and so on, because I won't look at stuff that's already in visited set, which might be problematic as well. How would you know that it's in the visited set? But let's say you can do it, then it's still n plus n minus 1 plus n minus 2, and so on. That's also, as I hope you know, O of n squared. So a fancier implementation is we have heaps now, so we can use them. So what you can do is you can say, okay, so and I won't do it today, but basically say, all right, like if you see a way to get from the visited set to a new node, just stick it in the priority queue, with the priority being the cost. And then when you're asking which node should I add to the visited set next, the answer is, well, the one with the lowest priority. Does that make sense? And that will turn out to be this much. So E log V. So we'll see how next time. So like with the dynamic programming things, what we figured out with Dijkstra is D of U for every node U. So what is the cost of the cheapest path from the source to U? That doesn't tell you what the actual path is. But once, just like with dynamic programming, once you know D of U for every U, you can figure out the path, right? So one thing you can do is you could just record as you go what is the path that that you should take, right? So in addition to saying D of V is this much, when you're adding V to the visited set, you're also going to say, and the where got to V is through U. So I'll have this additional data point, which is like, what was the previous node to V? And you're going to say, well, that was U, and you're going to add it as you're computing D of V. If you know the previous node for every node, you can, like, once you've computed everything, you can just go to the previous until you get to the source, and that's your path. Does that make sense? So, okay. So I think we are out of time, but we'll do this briefly on correcting. All right. So office hours as announced on Piazza. Abstract flip glasses. One of them are kind of crumpled up, but over here, first come, first serve. I will see you. Thanks.